Welcome to this coding walkthrough. In this session, we will explore the problem number 493, reverse pairs. We'll dive into the problem statement, analyze its challenges, and break it down step by step to uncover an efficient solution. Let's get started. In this problem, you are given an integer array called nums, and your goal is to identify and count all the reverse pairs in the array. A reverse pair is defined as a pair of indices, I, j, such that I is less than j, and the value at index I is greater than twice the value at index j. Essentially, you're looking for pairs where the relationship nums, I, 2 nums, j, holds true. For example, if the array is 1, 3, 2, 3, 1, you would need to identify all such pairs that satisfy this condition. The input format for the problem is straightforward. You'll be given an integer array nums with a length between 1 and 50,000. The output will be a single integer representing the total count of reverse pairs in the array. To help illustrate, let's take a look at some specific examples. In the first example, the input array is nums equals 1, 3, 2, 3, 1, and the output is 2. This means there are two reverse pairs in the array. The first pair is 1, 4, where nums, 1, is 3 and nums, 4, is 1. Here, 3 is indeed greater than 2 1. The second pair is 3, 4, where again nums, 3, is 3 and nums, 4, is 1, satisfying the condition that 3 2 1. Similarly, in the second example, the input array is nums equals 2, 4, 3, 5, 1, and the output is 3. This time, there are three reverse pairs, which we'll break down next. For the second example, the first reverse pair is 1, 4, where nums, 1, is 4 and nums, 4, is 1. Here, 4 is greater than 2 1. The second pair is 2, 4, where nums, 2, is 3 and nums, 4, is 1, and this also satisfies the condition 3 2 1. Finally, the third pair is 3, 4, where nums, 3, is 5 and nums, 4, is 1, as 5 2 1. The problem also comes with specific constraints. For instance, the array's length can be as large as 50,000, and the values in the array can range from -2 billion to +2 billion. Additionally, there are some edge cases to consider. If the array has only one element, there cannot be any pairs, so the output is 0. If all elements are the same, or if the array is sorted in strictly increasing order, there will also be no reverse pairs. On the other hand, if the array is sorted in strictly decreasing order, you may find a larger number of reverse pairs. Understanding these cases will help you approach the problem more effectively. To begin, the brute force approach provides a straightforward way to solve the problem by directly following the problem definition. Here, we iterate over all possible pairs of indices, I, j, where I is less than j, and check if the condition nums, I, 2 nums, j, holds true. The algorithm uses two nested loops. The outer loop picks each index I from 0 to n1, and the inner loop checks all subsequent indices j from I plus 1 to n1. For every valid pair, we simply increment a counter. While this approach is intuitive and uses no extra space, it is computationally expensive. With its n squared time complexity due to the two nested loops, it becomes impractical for large arrays, even though it requires only 1 space. The brute force method, while easy to implement, has significant performance limitations for larger inputs. Its n squared complexity makes it inefficient and unsuitable for scenarios where the array size is large. A more efficient alternative is the merge sort approach, which utilizes a divide and conquer strategy. This approach leverages the condition nums, I, 2 nums, j, by breaking the problem into smaller pieces, solving them independently, and then combining the results during the merge step. A key observation here is that dividing the array into smaller, sorted subarrays makes it easier to count valid pairs, as we can use the sorted order to our advantage during the merge step. This reduces the computational overhead significantly compared to the brute force method. The merge sort approach works in two main phases, splitting and merging. In the split phase, the array is recursively divided into smaller subarrays until each subarray contains only one element. Then, during the merge phase, we focus on two tasks. First, for each pair of subarrays, we count the number of valid pairs, I, j, where nums, I, 2 nums, j. This is efficiently done using two pointers, given that the subarrays are already sorted. Second, we merge these subarrays back together into a single sorted array. The total count of reverse pairs is aggregated during these merge steps. This method has a time complexity of O(n) log n, as the array is divided into halves recursively, and merging each half takes linear time. It requires O(n) space for temporary arrays during merging. Though more complex to implement than brute force, this approach is far more efficient, especially for large inputs. Another efficient method is to use a binary index tree, or bit, or alternatively, a segment tree. This approach processes the array in reverse while maintaining a frequency table of elements we've already traversed. The intuition is that, for each element nums, j, we can quickly count how many elements in the frequency table satisfy the condition nums, I, 2 nums, j, using range queries. After counting, we update the frequency table with the current value, nums, j. This method achieves O(n) log n time complexity, as each update and query operation in the bit or segment tree takes O log n, and we perform one operation for each element. However, this approach also requires O(n) extra space to store the tree structure. The bit or segment tree approach is competitive with the merge sort method in terms of time and space complexity, but it introduces additional challenges. These tree-based structures can be more complex to implement and debug, which may make them less desirable in certain scenarios. After evaluating the options, the chosen strategy for solving this problem is the merge sort approach. This is because it provides a good balance between efficiency and simplicity. With O(n) log n time complexity, it is significantly faster than the brute force method and comparable to the bit/segment tree approach. Additionally, the divide and conquer structure of merge sort is easier to understand and implement, particularly in environments where clarity is important, such as technical interviews. While the merge sort approach requires O(n) extra space for temporary arrays during merging, this trade-off is acceptable given its overall efficiency and simplicity. On the other hand, while the bit or segment tree approach is equally efficient, its added implementation complexity makes it less favorable. Tree structures can be harder to maintain and debug, which is a critical consideration for interview settings where time and correctness are key. In conclusion, the merge sort approach emerges as the most practical choice. It achieves a strong balance between performance and implementation clarity, making it ideal for both competitive programming and real-world applications. By leveraging the sorted order of subarrays during the merge step, it optimizes pair counting effectively while remaining straightforward to code. The problem asks us to find all pairs of indices, I, j, in an array nums such that I is less than j and nums, I, is greater than 2 nums, j. The goal is to calculate the number of such pairs efficiently. To tackle this, we will first explore the brute force approach to gain intuition for the problem, and then identify its limitations. From there, we will transition to a more efficient solution using the merge sort algorithm. Starting with the brute force method, the idea is simple. For every pair of indices in the array, we check if the given condition holds true. While straightforward, this approach can become computationally expensive, especially for larger arrays, as it involves examining all possible pairs one by one. In the brute force approach, we begin by initializing a counter, count, to 0. This counter will keep track of the number of valid pairs. Then, we use two nested loops to iterate through all possible pairs of indices in the array. The outer loop iterates over I from 0 to n1, while the inner loop starts from I plus 1 and goes up to n1. For each pair, I, j, we check if the condition nums, I, 2 nums, j, is satisfied. If it is, we increment the count. Finally, after all pairs have been checked, we return the value of count. In terms of complexity, this approach has a time complexity of O(n) squared, since it involves two nested loops, and a constant space complexity of O(1), as no additional data structures are required. While simple to implement, the quadratic time complexity makes this method inefficient for large input arrays. To improve efficiency, we turn to an optimized approach using merge sort. The key insight here is to leverage the properties of a sorted array to count valid pairs during the merge step. When we divide the array into two halves, any valid pair, I, j, where I less than j must fall into one of three categories. Both indices are in the left half, both are in the right half, or one is in the left half while the other is in the right. The merge step is where we count these crosspairs, specifically the third case where I is in the left half and j is in the right. The approach involves recursively dividing the array into smaller subarrays until each subarray contains only one element. During the merge step, we count valid pairs by using two pointers, P1 and P2, to traverse the left and right halves. For each element in the left half, we move P2 in the right half until the condition nums, I, 2 asterisk nums, j, no longer holds, and the remaining elements contribute to the count. After counting, the two halves are merged into a sorted array, ensuring that the sorted order is maintained as we move up the recursion stack. Analyzing the complexity of the merge sort approach, the time complexity is O, an asterisk log n, dominated by the divide and conquer process of the merge sort algorithm. The space complexity is O, n, as we require temporary arrays to store the sorted subarrays during the merge step. The efficiency of this approach comes from the fact that sorting the array reduces the number of comparisons needed to count valid pairs. During the merge step, the sorted order allows us to efficiently skip unnecessary comparisons by advancing pointers based on the condition. This divide and conquer strategy breaks down the problem into smaller, more manageable subproblems, making it significantly faster than the brute force method for larger arrays. It's crucial to handle edge cases as well. For example, if the array is empty or contains only one element, the output is 0 since no valid pairs exist. If all elements in the array are equal, the count remains 0 because the condition nums, I, 2 asterisk nums, j, cannot be satisfied. For arrays with negative numbers, the implementation must ensure that comparisons correctly handle the sign of the numbers. To illustrate the merge sort approach in action, consider the input array nums equals 8, 4, 2, 1. First, we divide the array into two halves, 8, 4, and 2, 1. These halves are further split into 8, 4, 2, and 1. Starting with the smallest subarrays, we merge 8 and 4. Since no pairs satisfy the condition, the count remains 0, and the merged result is 4, 8. Similarly, merging 2 and 1 gives a count of 1, as 2, 2 asterisk 1, and the merged array is 1, 2. Finally, we merge 4, 8 with 1, 2. Here, we find four valid pairs, 8, 2 asterisk 2, 8, 2 asterisk 1, 4, 2 asterisk 1, and 4, 2 asterisk 1, bringing the total count to 5. The merged array is 1, 2, 4, 8. This example demonstrates how the merge sort approach efficiently counts pairs while maintaining a time complexity of O, n asterisk log n. Here, we are implementing the solution using a divide and conquer approach with a modified merge sort. We start by defining a helper function called merge_sort, which will handle the recursive sorting and counting. The base case checks if the range contains 1 or 0 elements, in which case there are no reverse pairs to count, so it simply returns 0. Next, we divide the array into two halves by calculating the midpoint. The recursive calls to merge_sort process each half, and the results are added together to keep track of the reverse pairs found within the left and right segments. Then comes the critical part, counting reverse pairs that span across the two halves. For this, we use two pointers, I iterates over the left half, and j starts at the beginning of the right half. For each I, we increment j as long as the condition for a reverse pair, where nums, I, is greater than twice nums, j, is satisfied. The difference between j and the starting index of the right half gives us the count of valid reverse pairs for the current I. Once this counting is done, we proceed to the merge step, where we combine the two halves into a sorted order. A temporary list is used to store the merged values, and comparisons between elements in the two halves determine the order in which they are added to the list. The merging process continues here. If there are still elements left in the left half after the primary comparisons, we append them to the temporary list. Similarly, if any elements remain in the right half, they are also appended. Once the merging is complete, we write the sorted elements back to the original nums array for the current range. This ensures that the array remains sorted within the processed segments as we move up the recursion stack. Finally, the merge_sort function returns the cumulative count of reverse pairs for the range it was responsible for. At the end of the process, the merge_sort function is invoked for the entire array, starting from index 0 to the last index, effectively initiating the recursive sorting and counting process. The total number of reverse pairs in the array is returned as the result of the reverse pairs function. This approach efficiently combines the divide and conquer strategy with the counting logic, ensuring that we solve the problem in O, n log n, time complexity. In this implementation, we are solving the reverse pairs problem using a modified merge sort approach. The main method, reverse pairs, takes an array of integers and calls the helper method merge sort and count, passing the array along with the start and end indices. Within merge sort and count, we first handle the base case where the subarray has one or no elements by simply returning 0, as there are no reverse pairs in such a range. Next, we calculate the midpoint to divide the array into two halves. The recursive calls to merge sort and count process the left and right halves separately, and their results are added together to form the initial count of reverse pairs. After that, we calculate the number of reverse pairs that span across the two halves. This is done by iterating through the left half and using a pointer j to find elements in the right half that satisfy the reverse pair condition. For each valid pair, we update the count. Finally, we prepare to merge the two halves into a single sorted array. Once the reverse pairs spanning the two halves have been counted, we proceed to merge the two sorted subarrays. The merge method is responsible for this step. Here, we create a temporary list to store the merged elements. Two pointers, I and j, are used to traverse the left and right halves respectively. As we compare elements from both halves, the smaller element is added to the temporary list and the corresponding pointer is advanced. If one half is exhausted before the other, we simply add the remaining elements from the non-empty half to the temporary list. This ensures that the merged result is sorted. Once the merging is complete, we copy the sorted elements from the temporary list back into the original array, starting from the start index. This step is critical as it prepares the array for further merging and counting during the recursive calls. Finally, the merge process concludes by iterating through the temporary list and updating the original array with the sorted values. With this, the merge operation for the current subarray is complete. The recursion will continue to work its way back up, merging larger and larger subarrays while counting reverse pairs at each step. The overall approach leverages the divide and conquer strategy of merge sort, ensuring that the algorithm is efficient with a time complexity of n log n. This method not only sorts the array but also counts the reverse pairs in a structured and optimized manner, making it well suited for handling large input sizes. To solve the problem of counting reverse pairs, we start by initializing our merge sort function with the full range of the array, which in this example is from index 0 to 4. The first step in the merge sort process is the divide phase, where we recursively split the array into smaller subarrays. Here, we divide the array into two halves, one spanning indices 0 to 2 and the other spanning indices 3 to 4. We continue splitting the first half, breaking it further into two smaller ranges, 0 to 1 and 2 to 2. The range 0 to 1 is split yet again into 0 to 0 and 1 to 1. At this point, both subarrays are base cases, each containing a single element, so we return 0 and begin merging. During the count phase, we compare the elements in 1 and 3. Since there are no reverse pairs, the count remains 0, and we merge these two elements into 1, 3. Next, we process the single element subarray 2 from range 2 to 2, which is already sorted. Comparing across 1, 3, and 2, no reverse pairs are found since all elements in 1, 3 are less than or equal to twice 2. We then merge these subarrays to form 1, 2, 3. Shifting our attention to the second half, which spans indices 3 to 4, we split it into two single-element subarrays, 3 from 3 to 3 and 1 from 4 to 4. Both are base cases, so we return 0. Now, we compare these two elements. Here, 3 forms one reverse pair with 1, since 3 is greater than 2 times 1. The count increases to 1, and we merge these two elements into 1, 3. Finally, we compare the two merged subarrays, 1, 2, 3, from the first half and 1, 3, from the second half. As we compare across the two, we find two reverse pairs, 2 with 1 and 3 with 1, where both satisfy the condition of being greater than twice the element in the other subarray. This adds 2 to our count, bringing the total to 3 reverse pairs. After merging these two halves, we get the fully sorted array 1, 1, 2, 3, 3. The total count of reverse pairs in this example is therefore 3. For the second example, the array is 2, 4, 3, 5, 1. As before, we begin by calling merge sort on the full range, from index 0 to 4, and split the array into two halves, indices 0 to 2 and 3 to 4. For the first half, we divide it into 0 to 1 and 2 to 2, and further split 0 to 1 into 0 to 0 and 1 to 1. Both are base cases, so we return 0. In the count phase, we compare elements in 2 and 4. Since there are no reverse pairs, the count remains 0, and we merge these elements into 2, 4. The subarray 3 from range 2 to 2 is already sorted. Comparing across 2, 4, and 3, we find no reverse pairs, so the count remains 0. We then merge these subarrays to form 2, 3, 4. For the second half, spanning indices 3 to 4, we split it into 5 and 1. Comparing these two, there is one reverse pair, 5 with 1, since 5 is greater than 2 times 1. The count increases to 1, and we merge these two elements into 1, 5. Next, we compare the merged subarrays 2, 3, 4, and 1, 5 to count reverse pairs across the two halves. Here, we find 3 reverse pairs, 2 with 1, 3 with 1, and 4 with 1, each satisfying the condition of being greater than twice the element from the other subarray. This adds 3 to the count, making the total count 4. After merging these two halves, the fully sorted array becomes 1, 2, 3, 4, 5. Moving to the third example, with the array 5, 4, 3, 2, 1, we again begin by calling merge sort on the full range from 0 to 4. We split this into two halves, 0 to 2 and 3 to 4. For 0 to 2, we split further into 0 to 1 and 2 to 2, and then 0 to 1 is split into 0 to 0 and 1 to 1. Both are base cases, so we return 0. During the count phase, we compare elements in 5 and 4. Since 5 is greater than 2 times 4, we find one reverse pair. The count increases to 1, and we merge these elements into 4, 5. The subarray 3 from range 2 to 2 is already sorted. Comparing across 4, 5, and 3, we identify two reverse pairs, 4 with 3 and 5 with 3. This adds 2 to the count, bringing the total to 3. We merge these subarrays to form 3, 4, 5. For the second half, spanning indices 3 to 4, we split it into 2 and 1. Comparing these, we find one reverse pair, 2 with 1. The count increases to 4, and we merge into 1, 2. Finally, we compare the merged subarrays 3, 4, 5, and 1, 2. Here, we find 6 reverse pairs, 3 with 1, 4 with 1, 5 with 1, 3 with 2, 4 with 2, and 5 with 2. This adds 6 to the count, making the total count 9. After merging, the fully sorted array is 1, 2, 3, 4, 5, and the total number of reverse pairs in this example is 9. To analyze the time complexity of the solution, we start by examining the modified merge sort algorithm used to solve the problem. First, the array is recursively divided into two halves until we reach base cases of single elements. This process of splitting occurs log n times, where n is the size of the array. Next, during the merge step, reverse pairs are counted. For each element in the left half, we iterate through the right half, but the index for the right half does not reset, making the total work proportional to the size of the subarray being merged. This counting operation takes n time at each merge step. Finally, the actual merging of the two sorted halves into a single sorted array also takes n time for each merge. Together, these steps form the foundation of the algorithm's time complexity. When combining all the steps, the overall time complexity is determined by the recursive splitting, which occurs over log n levels, and the n work performed at each level for counting and merging. This results in a total time complexity of n asterisk log n. Now, looking at space complexity, there are two components to consider. First, the recursion depth is log n, so the recursive stack space usage is log n. Second, each merge step requires a temporary array to store the merged result, and its size is proportional to the subarray being processed, requiring n space in the worst case. When we sum these two components, the overall space complexity becomes n, due to the dominance of the temporary array space usage. Considering the best, average, and worst cases, we observe that the time complexity remains consistent. In the best case, such as when the array is already sorted, the algorithm still performs the same number of splits, reverse pair counting, and merges, leading to n asterisk log n. Similarly, in the average case, the overall structure of the algorithm does not change, so the time complexity remains n asterisk log n. In the worst case, when the array is sorted in descending order, the algorithm still processes the same number of splits and merges, resulting in the same time complexity of O n asterisk log n. When compared to the brute force approach, which checks each pair of elements in a nested loop and has a time complexity of O n squared, the modified merge sort is significantly more efficient, reducing the complexity to O n asterisk log n through its optimized counting during the merge process. To formally prove the time complexity, we used the recurrence relation for the merge sort algorithm, T n equals 2 asterisk T n/2 plus O n. Here, the O n term accounts for the work done during counting and merging. Applying the master theorem for divide and conquer recurrences, with A equals 2, B equals 2, and F n equals O n, we find that the solution to the relation is T n equals O n asterisk log n. For space complexity, the temporary array used during merging, requiring O n, dominates the recursive stack space, which requires O log n. As a result, the overall space complexity is O n. This balance of time and space efficiency highlights the advantages of the modified merge sort algorithm over the brute force approach. In this section, let's discuss some common mistakes candidates make when solving the reverse pairs problem and how to address them. First, not handling edge cases is a frequent oversight. For example, if the input array is empty or contains only one element, the solution might crash or produce incorrect results. To avoid this, always include checks for these edge cases at the beginning of your implementation. Next, ignoring the constraints on time complexity is another pitfall. A brute force approach using nested loops might seem straightforward, but it's inefficient for larger inputs and will likely result in a time limit exceeded error. Instead, it's crucial to analyze the input size and constraints to choose an optimized approach, such as divide and conquer. Lastly, mistakes in implementing techniques like binary search or divide and conquer, such as off-by-one errors or incorrect condition checks, can lead to wrong results. To fix this, take time to carefully debug your code, test it with small examples, and even work through the logic on paper before running it in code. Now, let's look at additional mistakes to watch out for. Losing track of indices when using two-pointer approaches is a common issue. Mismanaging how pointers move can lead to skipping over or double-counting elements. To prevent this, define clear rules for how each pointer is updated, and rigorously test your solution with edge cases to ensure correctness. Another mistake is unintentionally modifying the input array. Some solutions rely on preserving the original array, but candidates might sort or alter it in place, which can break the logic of the algorithm. If your solution requires sorting or modifying the data, it's safer to create a copy of the array and work with that instead of altering the original input. To perform well in interviews, there are a few key insights to keep in mind. First, interviewers often expect candidates to focus on optimal solutions. While a brute force approach may be a good starting point, you should aim to improve upon it and clearly explain the trade-offs in time and space complexity. Thinking out loud is also crucial. Communicate your thought process, especially when developing optimizations like divide and conquer or binary search. Additionally, use test cases strategically. Start by verifying simple inputs to ensure correctness, then move on to edge cases and larger datasets to demonstrate the robustness of your solution. Recognizing patterns is another important skill. Problems that involve condition checks across pairs or subarrays often benefit from techniques like divide and conquer, binary search, or advanced data structures such as segment trees. If you want to practice similar problems, consider LeetCode 327, 315, and 560, which involve related techniques or insights. Finally, let's explore some alternative approaches to solving the reverse pairs problem. The brute force method, which has a time complexity of O in superscript 2, is the most straightforward. While it's easy to implement, it's inefficient for large inputs. A better alternative is the divide and conquer approach, which leverages merge sort-like logic to count pairs efficiently in O n log n time. This method is more complex to code but meets the time complexity requirements for larger datasets. Another option is binary search, which involves sorting the array and using binary search to identify valid pairs. This approach also has a time complexity of O n log n, but it may require extra space for storing sorted copies of the array. Lastly, the two-pointer method can be effective, especially for sorted arrays, as it allows you to scan for valid pairs in linear time. However, this method requires pre-processing, such as sorting the array, and careful management of the pointer movements to avoid errors. Each approach has its trade-offs, so it's important to choose the one that best balances complexity and efficiency for the given input size. Thank you for joining this coding session. Today, we reviewed problem number 493, reverse pairs, and discussed the brute force approach as a starting point. Remember, understanding the basics is critical before diving into optimized solutions. Don't forget to practice similar problems, and we'll see you in the next walkthrough. Happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!